Hello, my name is Gary Allen, and in this video I will be presenting my final year project titled The Development of a PocketQube Satellite Communication System, which was done under supervision from Dr. Barnard. The goal of this project was to design and implement a wireless communication system for small satellites called PocketQubes. The PocketQube standard is one that aims to make it easy for various modules to integrate into one satellite enclosure. As an example, a PocketQube may contain a communication module, a sensor module, and a power module. This enclosure can then be launched into orbit or attached to a high-altitude helium balloon, for example, where its purpose could be to take atmospheric sensor measurements. For this project, the goal was to develop a satellite ground station prototype that can mechanically track and receive telemetry from such a balloon satellite, to be released by the E&E department from Saldanha Bay up the west coast. The full flight path of this launch can be predicted using a free online tool called HabHub, and a 3D view of this is shown. With a few assumptions, such as that the system would track the balloon from Cape Town, the requirements of the project could then be drawn up. Some important requirements include a 120 kilometer range with mechanical tracking, a PocketQube conforming communication module, a 3-hour running time, monitoring of telemetry via a user interface, and the capability to receive telemetry from so-called radiosondes, which are commercial atmospheric sensor devices used on weather balloons. Lastly, since an antenna mount was available, which catered for the mechanical side of the ground station, all components should integrate with it appropriately. I started by investigating the various satellite tracking methods available. The first and simplest method is sometimes referred to as open-loop tracking. Here, the ground station simply follows the predicted flight path. This method is very simple, but can be inaccurate up to 20 kilometers for a typical balloon flight, making tracking with a narrow beam width difficult. GPS tracking acts as a method of closing the loop, where the satellite transmits its GPS location, either directly or through a relay network as shown here. This has the disadvantage of higher complexity, but results in high pointing accuracy. Signal strength tracking was also considered, where the sky is scanned for the signal of interest to find the best pointing direction. Here, conical scanning is shown. This method provides great flexibility, but is also more complex to implement. I then consulted literature on the different types of antennas that may be used. A table comparing the general characteristics of the investigated antennas is shown. The half-wavelength dipole, quarter-wave monopole, helical, Yagi-Uda, and microstrip antenna types were considered. Dipole and monopole antennas are two types generally used when a close to omnidirectional radiation pattern is desired, such as on a satellite, whereas Yagi-Uda and helical antennas are often used when unidirectional higher gain antenna is required, such as on a ground station. I lastly looked at a few modulation techniques generally used in satellite communication. Most notable is LoRa modulation, which is a relatively new technology that makes use of frequency-varying chirp signals, ultimately allowing for a much lower signal-to-noise ratio at the expense of higher bandwidth. Research was also done to find the possible attenuation effects to consider in a link budget, such as path loss, cable loss, antenna mismatch, etc. A high-level diagram of the design system is shown. At the range of 120 kilometers, it was calculated that open-loop tracking would be sufficient if an antenna with a beam width larger than around 30 degrees was used. Closed-loop tracking could then be added later. The system frequency was chosen to be in the 433 MHz band, close to the 405 MHz radio sonde. A typical baud rate of 9600 was designed for, and LoRa was decided on as the modulation technique. The ground station therefore includes a microcontroller, a LoRa communication module, a GPS and IMU for positioning, a motor driving circuit to steer the directional antenna, a GPS and LoRa antenna, a power section, and an interface to a computer for monitoring. On the PocketQube side is the same RF and GPS module, a microcontroller, and a GPS and LoRa antenna. The designed PCB for the ground station and the PocketQube is shown. I then estimated a link budget, which allowed calculating the gain required from the ground station antenna to maintain a link margin of around 10 dB, as recommended in literature. The helical antenna was chosen over the Yagi-Uda since it would be easy to manufacture, and since these antennas typically have high bandwidth, which would make it easier to receive from the radio sonde frequency. One of the largest challenges I faced was catering for the large wavelength of interest, which is around 70 centimeters. Since the provided antenna mount was relatively small, the ground plane for the helical antenna could not be as large as literature recommended. FECO simulation software was therefore used to determine which combination of center frequency, ground plane diameter, and number of turns would provide the best performance given these constraints, and the final simulation results are shown. For the PocketQube, I decided on a simple half wavelength dipole, since it would be easy to manufacture and it was a familiar option. This design resulted in a final margin of around 13 dB. I designed the ground station software to cater for both open loop and closed loop tracking, while the PocketQube was simply set up to continuously transmit its GPS location. An overview of the tracking algorithm is shown. Essentially, this flow diagram shows that the ground station follows the predicted path until the GPS location is received. This received location is then used for a trust period of 60 seconds, where the system then falls back to the predicted path if the received location expires. Since stepper motors were readily available, the number of steps was used to determine the current angle in an open loop manner. Since the motor drives are dependent, however, rotating the azimuthal gear while holding the elevation gear fixed actually causes both azimuth and elevation angles to change, as shown. This must be compensated for. The relevant transfer functions and control formula were therefore derived, as shown. Finally, it should be noted that the ground station is calibrated with a so-called dead reckoning fix, where it is positioned with an external compass and a zero sensor, and a statically stored magnetic declination value is used to face it towards true north. The final ground station PCB and antenna are shown. Notable components used are the ESP32 microcontroller as well as the RA02 LoRa module. The PocketQube PCB was implemented with the Atmega 328 microcontroller and can be seen mounted onto a LiPo battery with a USB programmer to its left. Power tests were done as well as throughput tests, and these include tests to determine the current consumed by the motor versus speed, tests to determine the transmit power consumption on the PocketQube, and throughput bitrate tests, which showed the system successfully operating at above 9600 baud for the designed LoRa parameters. The GUI was tested to ensure both that the ground station could be controlled and that telemetry could be monitored. The image on the left shows the output after calibrating the ground station, while the image on the right shows the system receiving telemetry from the PocketQube. The helical and dipole antenna return losses were both measured using a network analyzer to ensure both had been matched to 50 ohms appropriately. The helical antenna showed a match with a null that was worse than the simulated match compared here. This was assumed to be due to the rough construction process used. It was decided not to optimize this since the mismatched loss was still acceptable for a system prototype. The dipole match showed a very good broadband match as simulated. I then drove to various locations to measure the system's range capabilities. With the PocketQube transmitter on Table Mountain, the final test was done at 122 kilometers range at Vredenburg, shown as the orange marker. The received signal strength indicator, or RSSI, value was then plotted as a function of distance. The telemetry was successfully and reliably received for all distances up to 122 kilometers, with an estimated margin of around 11 dB. Finally, I tested the various tracking methods. The mapped RSSI values of the closed loop test are shown. Unfortunately, it was not feasible for the department to fly balloon satellites this year. However, I managed to contact the weather station at Cape Town International and successfully tracked one of their radio songs. The predicted and actual flight paths of this tracking are shown. It is clear that the system managed to successfully satisfy all the requirements laid out in the beginning of the project, namely the range, monitoring, and tracking requirements. The system demonstrates a proof of concept ground station prototype which future projects can build on. Some improvements include a helical antenna manufactured with stricter tolerances, a deployable antenna for the PocketQube, the implementation of signal strength scanning, and a full PocketQube assembly. So this is just a demonstration. The calibrate button was just pressed there and the mount turns to face north, and then a flight path is uploaded to point from Stellenbosch to Table Mountain. This is from Constantia. There's a map reference on the ground, and the whole tracking starts at 3400 and ends at 3410. This is the closed loop GPS tracking, just following me running through the fields there. And finally, this is the 122 kilometer range test in Vredenburg. As you can see, it was extremely windy on the day. Thank you very much.